Welcome to the Science News Connection. We have several fascinating stories for you and the hottest news of the day. First off, we're going to tell you about a little boy. Or should I say a young boy, because he is certainly not little. His story has shocked the everyday person, the media, and even scientists. This is Dana Hoekstra, pregnant with a little baby boy. It was the year 2005 when the Hoekstra boy was born, and his growth was unbelievable.
Hi, I'm Liam. I'm 19 months old, and I have ginormous muscles.
At a young age, he could do sit-ups and had a six-pack that made the girls go wild.
Liam, you are so fine.
A quick look back into young Liam's past reveals a family history of fitness finesse. His grandfather was a construction worker who could lift boulders that usually took the strength of a whole crew.
I lift heavy stuff all day.
Liam's mother had been a professional athlete.
I like to run. I like to jump. I like to kick things. I like to punch things.
After doctors began genetic testing on Liam, they found that he had a very unusual genetic mutation. The mutation that caused his increased muscling was found on the gene that codes for myostatin. Normally, myostatin acts to counter the action of other genes that drive myoblasts, the cells that make new muscles. In the average animal or human being, myostatin keeps muscle growth in check. However, Liam isn't the first to have the mutation that inhibits myostatin. It has also been observed in various breeds of cattle.
My mama says that cows and me have this thing called
Musclin. Deep inside our bodies, we have this genetic mutation, and it won't let this thing called myostatin be produced. In Liam's case, and some cows' case, a deletion of certain genes results in an incomplete amino acid series to form instead of myostatin. The action of myoblasts is then left unchecked and muscles grow rapidly. Fortunately, this genetic mutation has had no adverse effects on Liam. The phenomenon occurring in Liam's body may greatly aid scientific research. The process that is now occurring naturally in his body could be replicated artificially and be used to prevent muscle wasting in patients ill with muscular dystrophy, cancer, or AIDS. But the problem is, where is the line drawn? Bodybuilders and athletes would pay big money to get their hands on this better-than-steroid drug. It would be almost impossible to test if athletes were using such a muscle enhancement. So how would we keep sports fair? But then again, some would say Liam Hoekstra was born with an unfair advantage. Imagine Liam Hoekstra, 10 years from now, amazingly fit and with the prime age to play sports competitively. With such an advantage, would he be barred from competing because of his natural talent? So what will happen to our little friend Liam? Will his condition further scientific research? Or will he leave his ordinary life and join the circus as a boy in a man's body? Now, a word from our sponsor.
Ever wanted to store your cells in a freezer? Yes. Ever wanted to help someone with a serious disease like Parkinson's or diabetes?
Yes.
Well, that's too bad, because it's not possible right now.
Aww.
But don't worry, scientists predict that this will all be possible in the near future.
3 cheers for stem cells! Hip hip hooray! Hip hip hooray! Hip hip hooray!
The possibility of stem cell research. Today, we're going to continue with a short segment about stem cell research currently going on in the world today. Please welcome Dr. Fitzgerald.
Oh, thank you all. Today we're looking into the potential of embryonic stem cells. They're like little factories, chugging out millions of cells.
Cool, man, but why is that useful?
Let's turn to Dr. Addison Montgomery to help us answer that question. Well, embryonic stem cells are cells that are not yet committed to becoming a particular organ. Stem cell biologists have shown that embryonic stem cells can actually become almost biological factories producing millions of any kind of cell. So, the goal is to be able to manipulate stem cells so that they can be expanded and used to replace brain cells for those who have Parkinson's disease, or so that they become islet cells for diabetics. With the great advances being made in stem cell research today, scientists can already see this day in our future.
Basically, in the future, we'll just use cells. We won't have to use drugs anymore.
Well, let's give our viewers some quick facts about stem cells before our next program.
The scientific community agrees that all stem cells are capable of limitless self-renewal. Also, they divide so that they produce one cell that's exactly like itself and another cell capable of becoming a different type of cell. Finally, they originate from other adult or embryonic stem cells. Stem cell research has only really taken off in the past few years. However, Dr. Ronald McKay made a discovery 9 years ago that may be used to cure Parkinson's disease in the near future.
In 2001, I was able to use mice stem cells to treat a disease like Parkinson's disease in mice. Quite interesting. Yes. Stem cells are basically amazing, but they're facing some heat from the dark side.
Why is that?
Well, most research done on stem cells uses embryonic stem cells, which are extracted from frozen embryos. Those who argue against stem cell research suggest that we use adult stem cells. However, there isn't enough adult stem cells to further research because they're only found 1 in 1 million cells in the body.
Fascinating. Well, unfortunately, that's all the time we have today. Thank you, Dr. Finkelstein.
Thank you.
And now we move on to our next program.
Next, we will hear a short report on deafness and its genetics. Here we see a family. The mother, deaf. The father, also deaf. But the child can hear the whooshing of the wind and the crunching of dry leaves on a cool autumn day. Now you may ask, why? This does not make any sense. Well, that's what we're here to explain.
Deafness arises from defects in the conductive, sensory neural, and central processing system. Deafness was one of the first physical disabilities that physicians examined.
Hey yo, Connexin 26 is found in more than 1/2 of profound deafness, and that's a fact.
Connexin is a protein necessary to make gap junctions. These junctions create channels between cells. Oh no! Mutations of this gene have been found in different ethnicities all around the world.
Now we're going to look at 2 different families. Both were affected by deafness, and we'll see how deafness is passed on or not passed on to their children. Here we see a couple. Surprisingly, their children will most likely not be deaf. They won't have the genetic makeup to cause deafness because it's a recessive disorder. So then what causes a child to be deaf? Well, here's a second couple.
Y'all, I can hear just fine, but lots of my relatives is deaf. And my hubby's here is deaf too, but he's just the sweetest.
Because the wife in this relationship has relatives who are deaf, she is probably a carrier of the deaf gene. Because deafness is a recessive trait, it does not manifest itself. However, the husband is deaf also due to genetic reasons, so their children will most likely be deaf.
For those people that want to avoid having a deaf child, there are solutions, like adoption or pre-implantation genetic diagnosis. However, at the same time, we still want to preserve the deaf community.
Well, that's all today. I hope you learned a lot tonight, and join us next time on the Science Hour.
Oh, science rules!